let's try to talk about model selection. So this came up before in many of our discussions, and anyone knows what we mean by model selection? So let's say in the context of regression, you have beta 0 and beta 1. 1 plus beta 2 x 2. That's beta 3 x t. And so this is like at the population level. And then you have sampling of this. So when we say model selection, what do you usually mean in this context? So remember we had like discussions of the F-test, use model, full model. Okay. So does that. So what is an F-test doing? Yes, so guess whether we should use the null model or the reduced model? Or the original. And the original full model, let's say. So for example, if I test whether like this hypothesis. Right. So if I call this model M, there is this model 0, model null. So what is the corresponding model for this hypothesis? Actually, that's the beta 0. Y is equal to beta 0. So this is the most basic model. I could test this hypothesis, for example, for beta 2 all the way to beta PR equal to 0. Okay. What will be the model here? What's the beta 1? Yeah, so beta 0 plus beta 1 is 1. And so I mean, it can go on. So I could have a different model. Right, just keep, let's say, x2, another model, and then just keep x3. And then you could have a model where we keep just m1 and m2. Sorry, the x1 and x2. And like one, like let's say 2, 3, 1 tree. And 2, 3. You can imagine what these are, right? So it takes only x1 and x3, x1 and x2 and x3, and then we'll have a model which is like 1, 2, 3, which contains all of these beta 0 plus beta 1, x1 plus beta 2, x2 plus beta x3 plus epsilon. So let's say P is equal to let's see, P is equal to 3. Yeah, so we have 3 covariates. But then you have this model, basic, and then you have these 3 models, and 3 models with 2 variables, and 1 model with 3 possible variables. Okay. So the idea of model selection is that, I mean, I want to pick among these models. The idea is that maybe some of these covariates are not contributing to Y. So I don't want to keep them in the model becomes simpler. And so if you view it in this way, all the things that we are doing was some sort of model selection. So the usual F-test that we did, a general F-test is testing between 2, like trying to compare 2 models and pick. It's like a binary model selection. The t-test is also like that. So you test whether I can set this equal to 0 or not. This is deciding between two different models. The more general idea is that I look at let's say all possible combination of the covariates, and among all these possible models, I want to choose which one. So if you try to do pairwise F test, we have done something like this, but this is also one of the ways, so we won't get to that. So there's a procedure called, for example, footwise regression that does that in a greedy fashion. But generally, you want to consider all of them together in a sense, and somehow you want to score them. The general procedure is like assign the score to them and then compare them based on the score. So you can try to do pairwise comparisons, which then requires you to do a lot more. So, maybe just my later first. Yeah, how many possible models do we have? Let's say if I have p variables, if I do this procedure, how many models do you think you will end up with? Yeah.
P factorial maybe?
P factorial. Why?
So you do like every combination.
If you do every combination, so p factorial would be if I like the number of permutations of p variables.
Oh,
This is the number of all possible subsets of. So, what is the number? Number of all possible subsets of. Let's say x1, x2, x3. So I have key variables. And I take a subset of them and I form a model. So the number of models is the same as the number of all possible subsets of the set of key elements. Anyone knows from combinatorics?
To the p power.
Sorry?
To the p power.
2 to the p, yes. And the answer is 2 to the p. There's exponential in p. In this case, p is 3 would be 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then if you have 4, you'd have 2 to the 4, which is 16. If you have 10, the 2 to the p would be and 24. If you have 30 covariates, this means the 3, right? Which is roughly like 20 to the 3 to the 3, which is a billion models. That's right. So this is like the exponential growth. So if you want to search, so if I'm going to do like pairwise comparisons, I'm going to have to do even more. So if you do pairwise, if this is like capital N, if I do pairwise comparison, I have to do n choose 2, which would be roughly n squared. It's even worse. So the number of pairwise comparisons that I have to do is whatever that number of models is to the power of 2 roughly. So the general idea is to try to assign some scores to these models, like classical approaches, and then compare them based on their scores. At least you compare like n of them. But if you start doing this, you'd see that it's going to become hopeless very soon. Okay, so if you see some of the procedures that I'm going to talk about would work for general P, but they're really feasible for small p. So what we can do is science companies models that convert them. Score. So in general, we end up doing all substance. So that's what we have as all substance. Regression. You compute the score for all possible subsets, for all possible models, and then decide which one has the best score, and then you declare it as the model.
Yeah, can we put it right here?
Yeah.
Are you using this side of the board?
No, I'm
No.
just gonna use if you manage to.
Yeah,
set it
I
up.
mean, we want to know where, so because some professors want to use this
No,
side.
no.
Okay,
just completely-
we'll just use this side.
Great, thank you. Um, So this is a general procedure, all subset regression, you can calculate the score for each model. And then we try to confirm the based on the score. So it's not gonna be feasible unless p is small. Let's say p is 3, there are 8 models, it's doable. P is like 10, maybe still doable. P30, bigger computer, P40, 50, 60, 100, it's like we can just do it as an exercise. Useful, find like how they do it. And we do all subjects together. Okay, so that's the first practical answer on the score. What are possible scores in science? You compare them all.
Other lines. No,
Yes.
so that are squared.
R squared, that's a very big candidate. So. R squared. 1. Right. So now, anyone has any objections to R squared as a score for comparing overfitting? Right? Overfitting. Overfitting, I think. So that's a good answer, but let's say you apply R squared in the to equation. Can you tell me which model is it based on R squared? So yeah, I'm gonna always pick this one. If I do R squared. Why? The most complex, but
Minimum FSE.
sorry,
Minimum FSE.
minimum SSE. So the point is this model contains all these other models as submodels. Okay. The fact that it's complex is not enough. So I can have a very complicated model based on different sets of covariates. And it could have a still higher, like a lower R squared than some of these smaller ones. The reason why this happens is because all these different models can be obtained as submodels of this. So there is this submodel relation. If I said, for example, theta 1 equal to 0 here, I get the model M3. If I set 2 equal to 0, I get M1 tree. Right? So if I set some of the coefficients of the linear model, so imposing constraints on the coefficients of this model gives me some of these other models. So all these other models can be obtained like that. So these are all submodels. So all submodels are M1 through 3. And so R squared M1 through 3 would be bigger than or equal to R squared M X, Y, Z for any X, Y, Z. for any of these models are squared at M1 P, it would be so if you go with this, you can always take the biggest one. And then we talked about overfitting. You don't necessarily always want to go with the biggest one. Because you can always keep adding values until you reach R squared of 1. The overfitting part is a little bit subtle. But there is often this idea that there is noise in the problem. And if your R squared is 1, you're explaining all the variation in Y, including the noise. You don't want to do, because the noise is going to change from instance to instance. So people come up with methods to try to break this submodel issue. And the idea is to try to balance the complexity with this of fit. So you want to get some form of complexity into your score. So the scores that have scores that take complexity into account. So for linear models, the complexity would be the number of parameters. Okay. That may not in general be a good measure, but for a linear model where the covariates are linearly independent, it's a very good measure. So this model, so if the covariates are linearly independent, this model is the most complex. These are in the second level of complexity. These are even simpler. This is the most simple. So people traditionally prefer to go with simpler models if the performance is similar. So if I'm like M1 and M12, if I compare them, let's say the R squares are close, the R squared of M12 is always going to be bigger than M1, but not too big. So then I can, if we go with the R squared of this is like 0.79, this is 0.78, I would prefer this model. So that's how these scores are built. The basic one is, anyone knows what the basic one is? The most basic, like I can like manipulate this a little bit. Sorry? Yes, adjusted R squared. So there's like a tiny adjustment to R squared that I can make to avoid paying this price. And so it would be like 1 minus SSE. I also want to write P here because it depends on the number of parameters, divided by n minus P minus 1, and then SSP divided by n minus 1. So you divide both the SSP and SSP by the degree of freedom. Okay. Another way of saying is like this is 1 minus MSE divided by, if you want to call it MSE, mean squared total. This also is equal to, these are all equal to S squared, which are our estimate of the noise variance. Okay, I'm going to call it also S squared P. So this SSP, or if you want to call it MST, is fixed for all these models, so it's not going to change. SST depends on the Y's, remember, so SST is summation I from 1 to n yi minus y r squared. So it's going to be the same for all these models. So this part, the denominator, does not change. So when I compare by r squared, I'm going to basically comparing by the small. So larger r squared adjusted is equivalent to smaller MSE or a smaller S squared. So comparing by r squared adjusted is the same as comparing by S squared. So we can choose based on the smallest R squared, like biggest R squared adjusted or smaller R squared. So the point is, there is this division by n minus p minus one. So if you just go with R squared, it's equivalent to R squared is one minus SSP divided by SSP. So the largest R squared is equivalent to smallest SSE. If you just go with SSE, the issue that I mentioned happens. Okay, so the largest small always has smallest SSE, but MSE takes into account the number of parameters. So you're dividing by the number of parameters. So it could be that SSE of this model is smaller, but n minus p minus one is also going to be smaller, right? Especially if p is very large, gets close to n, this gets very small. So when you divide SSE by this, it's going to become larger. So as p goes up, potentially SSE goes down, but n minus p minus one also goes down. And so the ratio is not necessarily going to go down, right? Especially when p approaches n, it's going to get very small, and so this blows up. So you're going to discount a larger model. So this is the simplest way that you can probably think about. Just divide SSE by n minus p minus one. Basically, you can like work with s squared. So that's one possible measure. Any questions about that? So this is always reported. Most people report it, and it's really easy. Just minor adjustment to. Choose for R squared adjusted is smaller. Sorry, higher, or S squared is smaller. Questions? Okay, the next measure is another way of scoring things. So that would be AIC. This is called. This is the name of the guy. I think it's information criteria. So this is fairly general. So we have a model where we have a likelihood. Let's say I would like to is. If you remember, it's like, so actually this is the log likelihood, which is like log e theta, let's say u1 x and y. Whatever the data you have is just a function of theta now. Once you get the log of the density, you do the function of theta, and then you have a maximum likelihood estimator, MLE, for model M. And so the likelihood usually is, for example, in this case, is defined for like the largest model in a sense. But then when I restrict the theta to different subspaces, I get different NLEs. So I'm maximizing this likelihood over different subspaces or different subsets of the space of theta. So theta here is like the same as beta for us. Yeah. So this is similar to beta in regression. So if you have an NLE for model M, so a restricted NLE, then so AIC is defined like this: negative to likelihood divided by this restricted NLE plus 2 times T of M, so the number of parameters. Okay, so this is a measure of how well the model fits, how good it fits, and this is a measure of the complexity, number of parameters of the model. So in regression, if you do it, so so you can write down, so this, in our case, just be theta would be between beta and sigma squared, for both of the parameters. And the likelihood, if you write it down, I don't want to probably write it. So you can write down the likelihood, you've done it for the, like under the Gaussian assumption, you can write down the likelihood. And then once you plug it in, this term becomes n log SSE. So basically, I'll do it, I'll do the regression, it's equivalent to doing the regression, finding the OLS. And S squared, but not the squared, you remember the MLE, the estimate of the MLE. So the MLE estimate of sigma squared was SC divided by N. So you have, so this for us would be, in the context of regression, would be beta hat OLS, and then sigma hat squared. This is the maximum likelihood estimate, which was a little bit different. So you plug it into the likelihood, what you get is, this is for the Gaussian case, n log SSET divided by N, and then plus 2 times E plus 1. E plus 1 is the number of parameters of the model. Okay. So the point is, so you really can do this calculation, it's pretty simple. The point is, again, I have a measure of how well it fits, which is dependent on SSE. And then I have a penalty here, which accounts for the number of parameters. So you want to basically minimize, right, the AIC. So you want this to be smaller. So it's smaller if SSE is smaller, or the number of parameters is smaller. So as you increase the number of parameters, SSE goes down, but this goes up, and so they balance the two out. So this gives you a general procedure, right? So that's AIC, and then we have an example here, and then there's also a Bayesian information criteria. Which is which we skip. It's very similar. So this is an example where, and in your book, where like they're trying to predict the yield of a power plant, and what we have is the so here so there are a bunch of variables, like probably 10, and so there are a lot of models, like probably 1,000, like 10, 24, but for each P here is the number of covariates you want to keep in the model is or they're plot, like they're reporting the 4 top models, the best top models. So the best 1 variable model, 4 of them, the best 2 variable models, the best 3 variable models, the best 4 variable models, and so on. And for each one, the best according to the criteria. Okay, some of the criteria. So all the criteria are listed. You have R squared adjusted. CP, I'm going to talk about AIC and S squared. Okay, and you can see, and then the variables are here. So EP, these are like different characteristics of the power plant that help you predict the yield. So what do we see? Like, how do you like interpret these results? Let's say. So if you look at the R squared, for example, you can see that generally R squared sort of increases. Okay, as you increase the number of variables, like so the best R squared is 0.86 for 10 variables. So this dominates everything else. Right, so the best that we can do is 8.6. But if you look at the R squared adjusted, you can see that starts small, goes up. Here, so the best, for example, among the 2 variable models is this one. The best among 3 variable models is it's sorted according to their properties. So the best is this guy, ESPP, And then 4 variables, and you can see like it goes up to a certain point, maybe 80 around here. If you look at the 6 variable model, you can see it's 0.80, and then remains around 80, 81 still, but 80, and then drops. Like, it doesn't go up dramatically, right? And especially for this larger one, it drops to 0.79. So you can see like the adjusted R squared is, for example, this is slightly bigger, but relatively stable. Okay. So compared to, for example, 67, there is a big jump when you go to 5 variables, like 67 goes to 79. But then at this point, it's like sort of mildly varying. They're all around 0.80, right? With this order. So you can go with the like 5 variable model or 6 variable model. But this is probably where you should stop. It's a little bit qualitative, but you can see when you can see a big jump, but then things are gradually improving or not improving at all. So the same goes if you look at AIC. AIC you want it to be small. So usually it's negative because it's negative log, like log of something, and the like SSE divided by n becomes small, and so things are negative. So more negative is better. So start from negative 78 and you go down, you can see it's like generally goes down to around 5, like 0.108, again 6 around negative 0.108, and you're like hitting this barrier, and then it goes up 1.6. Okay, so again, this suggests that maybe around 5 or 6 variables is good to stop. Okay, and the best one within each class is like so the difference is like this n. So either you go with 5 or 6. And the S squared is similar. So S squared, if you decide based on S squared, should be similar to R squared adjusted. I'm not going to go over it. You can verify the smaller one. So it gets smaller, 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 all the way to, you can see like there's a big difference here, but then not much difference. It's slightly like from this still like slight difference, but these are very similar. So not the first one. So you get a sense that around 5 or 6 variables is where you have to stop. Okay. Sounds good. So this gives you some simple ideas. Assume that you can actually do this calculation, which takes a long time. So they're not showing all the models. They've done it on all the models, but take the top 4 within each category. Questions about this? It's a rather simple way of doing things. There's this also this Mallows CP, which is an interesting quantity. Yeah, so this is related to some outliers. So if there is a case 21, we didn't talk about outliers, was discussed in the discussion. If you remove it, there's some rather improvement. So you can like manipulate. So take some data points out and then decide. So Mallows CP, let me maybe mention this rather quickly. So it's a criteria which is interesting in the sense that there's a bit of AIC also has some theoretical considerations, but this also has some theoretical considerations. The idea is that I can take up the general model, the true model as a submodel of the biggest possible model. So we have a true model, which is, let's say, just let's say, so y is like beta 1 x1 plus beta 2 x2 plus beta 4 x4, and then plus epsilon. But I have, let's say, 5 variables. So I can write this model as a submodel of this more general model. as we've seen before, x1, x2, x3, x4, x5, beta 1, beta 2, 0, beta 4, 0. Okay, so it's an instance of the general model, like x beta, where we have all the columns. Now I'm using Q here. I think your book does it. Q is all possible covariates that we have, not necessarily the ones that are going to go into the final model. Let's say P is the number of, or like P plus 1 is the number of true covariates. So Q is 5. This subset is sometimes referred to as the support of the coefficients. The true support is 1, 2, 4. Support is the location of the non-zero coefficient. So according to this sort of notation or like formulation, if I write the true model, it would be like x s star beta s star. So x s star just takes all the columns that are indexed by s star. Beta s star just removes these zeros. Just look at the coordinates of data that are indexed by s star. So the actual model is like y is x s star beta s star. So x s star is this. Just picks these columns. And beta s star is just the one that picks these rows associated with those. So this is really the actual model, but I don't get to see s star. So you can think of the problem model selection as trying to estimate or detect that s star. Once you have the s star, you can just do the regression, usual regression on those covariates, reduced covariates. So that's what makes the problem difficult, because at first I don't know the number. Even if I know like the three true variables, then I have to choose a subset of 3 out of this 5, which has combinatorial size. 5 choose 3, which is a large number. So I can do that, use the measures that we had. But Mr. CP, I mean, still I have to do the subset search, but Mr. Mallows, not Mr. CP, Mallows suggested to an interesting criteria. So any questions about the setup? So what did he propose? He proposed to assume, let's say I pick a subset S, the candidate S. So S is not necessarily a true subset. Let's say it has P plus 1 variables. You could drop 1, it's easy. But let's say it's P plus 1 because usually you have the intercept. So we fit this model of y is x sub S alpha plus S1. So x sub S is just the columns of the design matrix associated with subset S. So if I choose, for example, S to be 1, 2, 3, 4, x sub S would be just let's say, okay, 5 maybe. Would be x1, x2, x3, x5. So only the columns that are associated with that subset are picked. So I fit this regression, and I get a fitted vector of fitted values, which I'm calling mu hat sub S because it depends on S. So you get xs alpha hat. Alpha hat is just the least squares estimate in that model. Mallows proposed to look at this distance. So there is a true mu, the true mean vector, which is this guy, right? There's a true mean vector, and you can also call it the true mean vector as this as well, because in this notation we also have a bunch of zeros and beta, so this is the same as that. So I have a true mean vector, and I have an estimated mean vector, and then I would look at, okay, it takes a while. And then I would look at mu minus mu hat norm squared, the expectation of it divided by sigma squared. So this is a good measure because it's a measure of how well I predict. So mu is my prediction basically. So this is saying on average how well I predict relative to sigma squared. So Mallows looks at this and tries to rank the models based on sort of this distance. It's a form of rescaled MSE for parameter mu, let's say. Let's not get into that much, but this is the true mean vector, and this is mu hat. there are some issues with this. I'll show you what the result would be if you calculate this, but there's some issues that first I don't know mu and also don't know sigma squared. And I also, yeah, so I can probably take expectation in the land of theory. But let me maybe argue why this is an interesting measure. So Mallows tries to like choose the model or a subset S that minimizes this criteria. So why this is interesting is because once you write things down, which in the interest of time you probably should either do or do not. So what we can do is like we can write this down, the expectation, and it turns out to be this quantity. The way it works is you'd have this H matrix associated with, so this is the H matrix associated with X sub S. And what you do is like, I'm going to calculate mu hat S, which is going to be H S times Y. This is the same formulation. And then mu minus mu hat S would be, basically this would be Y minus epsilon minus HSY. And so you get I minus HS Y plus okay, no, I don't want to do this. I want to write it the other way. So mu minus HSY plus epsilon, sorry, mu plus epsilon. So I get I minus HS times mu minus HS epsilon. And so this is HS perp mu minus HS epsilon. And because HS perp projects onto the orthogonal component and HS projects onto the space, these are orthogonal to each other. So then I square things, and you do the square, you get minus, this squared would be HS perp mu squared plus norm HS epsilon squared. And then you take the expectation of both sides, this is constant, and then you can calculate the expectation of this. This is an example where you have, so if I take the expectation, so anyone knows what the expectation of this quantity is? Expectation of HS epsilon squared. HS is a projection matrix, epsilon is Gaussian. So epsilon is normal, which means zero variance or like covariance sigma squared I. So HS epsilon divided, sorry, perp epsilon divided by sigma norm squared. This has a particular distribution. Like, yeah. Yes, so chi squared with rank being, sorry, with degrees of freedom being the rank of HS perp. So what is the rank of HS perp? Oh, sorry, not perp, because we don't have a perp here. HS, we just have HS here. So what is the rank of HS? So HS is just the projection matrix associated with XS, and S has size P plus 1, so this is going to be P plus 1. Okay, and then the expectation of this would be the expectation of chi squared with P plus 1 degrees of freedom, which is P plus 1. So that's where P plus 1 comes from. Okay, and then if you square this expectation is not there because it's constant. So if you square this, use the property that HS perp is idempotent, you get the quadratic form Y transpose this squared Y. So once I divide it, so this is once I divide both sides by sigma squared, you get this sigma squared plus P plus 1. Okay, so the calculation you should be able to do. It was a little bit quick because we're out of time, but that expression is very interesting because what it's saying is there is this part which is always going to be there. It's the number of parameters that you picked, that choose to put in S. This part could be in there or could be not in there. So if mu is in this, like the image of XS, when I project it onto the common complement, what would I get? So if mu is in the image of XS, then I project it onto XS, like HS, basically HS mu. Mu would be equal to HS mu, which then means that HS perp mu is 0. So this quantity would be 0. So this distance would be exactly p plus 1. So if I have enough covariates in the model such that it explains mu perfectly, then this distance would be p plus 1. If I don't have it, if mu is not in the image of XS, so I haven't included enough covariates, then because this is a positive semi-definite matrix, HS is projected as positive semi-definite, this is going to be always non-negative. So it can't be 0. So it has to be positive. So this is going to be larger than p plus 1. So what happens when you calculate this Mallows CP, like population version, if the model is adequate, if you have included all the right covariates, then you hit p plus 1. If you haven't included all the right covariates, there's this term which is bigger, so you get something bigger than p plus 1. So by comparing this to p plus 1, you can see whether you have like included enough covariates, like the right covariates. So that was quick, but if you think about it, you can see. So if the model is adequate, you get p plus 1. If it's not like adequate, you get something bigger than p plus 1. And this allows you to decide. The only issue is that first, we don't know sigma squared, which we usually know how to deal with it. Second, this is expectation. This is not population version. And I don't know mu, so I can't calculate this distance. So what Mallows suggested is a very simple idea. So if you look at the expectation of the SSE, you know that this is the expectation of the residual squared. In this case, you have to write this down as we did. We don't know here in this case that mu is in the image of X, so there's this extra term that comes up. So as an exercise, try to calculate this. It's not like the case where we did for the regression where the model was correct. So in general, you would have like this would be mu plus epsilon, but mu is not necessarily in the image of XS. So you write down the expectation, and this turns out to come out. So because I have this, and I want to, if I divide by sigma squared, I get something which is very similar. So divide by sigma squared here. You can see it's like here is like p plus 1. Here I have n minus p plus 1. I can adjust this. So I can readjust. So if I add this quantity to both sides, I get p plus 1. So what he suggested is to look at SSE divided by sigma squared minus n plus 2p plus 1. So if you take the expectation of both sides of this, the expectation would be the same as this quantity that we had. So this is his idea. And then we don't have sigma squared. We don't have sigma squared, so we're gonna replace sigma squared with s squared. So at the end of the day, this is Mallows CP. So everything you can calculate. So if you had sigma squared here, this would be an unbiased estimate. So this is an unbiased estimate of the Mallows CP, and this is like an estimate of that unbiased estimator. And so in the end of the day, that's his criteria. You can see it's very similar to the things that we have seen before. So the first term is measuring, this part, let's say, or this part measures the goodness of fit, and there is a term which measures the complexity of the model. So you want to minimize this, but the idea is that there is like a minimum. So the advantage of this is that there is like a calibration. So you know where you hit the truth, then it is around p plus 1. So if you do it, for example, in this example that we had, so he's plotting, or they're plotting the CP, this estimated quantity, now CP, versus the number of parameters. So for each, let's say I have a 4-parameter model, and then I have 5-parameter model, a bunch of them, a 6-parameter model, a 7-parameter model, and you can see that they're really high. This is the line p plus 1. Okay, so eventually you're gonna come down and you hit this line p plus 1. And so this is probably a good place to stop. And you can see, once the model is adequate, you're gonna be around this p plus one. So the first time that you hit the smallest number of variables, you're gonna go with that, yes.
I thought you said that it couldn't, why can't it be below the line? I thought you said the other one could be. That when you're doing the teacher.
So this is always there, and this is always non-negative. So it is at most p plus one. So it can't be below p plus one.
And why were some of those points below the line?
Right, so why some of them are below this? You tell me. It's a good question. So it can be below the line, so why some of them are below the line? Contradiction. So that was for the population version. And assuming that the model is correct. Okay, so this is of the estimate. The estimate, there is some noise around p plus one. And furthermore, there's no reason why. So we started with, like, we assume that once you include all the covariates, like there is a subset that explains the model well. It could be that the linear model is not correct, but the main issue is like the variation due to the estimate. So we replace basically this expectation by itself. Okay, so if you had the expectation of this, it would be malloc CP. I like the population version, but we're removing the expectation. Okay. There is another measure, which is press statistic, which you've seen. I mentioned this. You've seen this in the when we had when Ian talked about leverage. So the idea here is like doing cross validation. So this would be leave one out. So a general approach is to do cross validation. Try to leave some of your data out. Try to predict the Y's for what you haven't seen. So if you do leave one out cross validation, which is I leave the I data point out, fit the regression model, so we give me y hat I as the prediction of the y for that data point that I haven't included in the model, and I know the actual y for that, and then you can compare. Because you haven't included that data point, this is really a genuine prediction of your model. Okay, and so these are called press residuals. These are not the same as original residuals. Original residual is including that data point in the model as well. But generally, these are going to be bigger than the usual residual. But the interesting thing is that these press residuals, prediction, I forgot what you call. There's a prediction involved. So this is like an acronym for something. The press residuals can be written as the actual residual divided by 1 minus HI, the diagonal of the H matrix, which are called the leverage scores, which have something to do with outlier detection. So this can be actually calculated without doing these individual regressions. You have to leave one out, do the regression again, and so on. In the linear regression, you just do the entire regression, and then you can calculate this press residual. And this can be used as a measure of model selection. This approach in general is called cross-validation, which is, and you can do it with leaving some bigger subset out. So you can do k-fold cross-validation, like split your data into the k parts, fit on k minus 1 piece, and try to predict the remaining piece, and then repeat by just shuffling the pieces around. So this is an interesting criteria very often used in machine learning to pick the models or hyperparameters of the models. And here we can do that as well. So you do it, you get some result in this case. Maybe just one more point out. There are the stepwise regression, as I mentioned, these are greedy approaches. So you start from, for example, no model. And so this applies to any other criteria that we have. This is a procedure to avoid the combinatorial explosion of the number of models. So instead of trying all the models, we do a greedy approach. We start with no variables, add one variable in. You can do it by any other criteria that we mentioned, the best one variable model. Or you could do it, for example, an F-test or a T-test. What happens if I add one more variable to the current model that we have, there's no variable, test all possible one variables, and the best one you include. Once you include it, it remains there. Now remove it from the pool of the variables, Now I'm gonna add one more variable, see among all the remaining one, which one is better. By some of the criteria we had or the F test, and then I add that in. Now I have two variables, I remove it from the pool and then check all the other ones. So if you do this, eventually, let's say if you do an F test, eventually you're not gonna reject any of adding any of the variables and you can stop there. Okay, or you can start from the full model, recursively remove one variable at a time. The idea is that these approaches avoid the combinatorial explosion. Okay, so because you're gonna at most choose p+1 in the first step, like test p+1, put one in there, and then the next step you have p remaining variables. You test all of them, you pick one, and then you have p-1. So if you do it, at most you have p squared, like operations. If you do like less than p squared, but of the order of p squared, rather than 2 to the p. So these are the methods that you can use. I mean, classical, and then there is a method which we unfortunately didn't get a chance to talk about, which is lasso, which is the modern way of doing things. And we talked a little bit about this. You do the L1 penalization, and it automatically picks the zero subset, like zeroes out a lot of the betas, and you figure out the right beta. For that, there is a very nice book I'll link on the hopefully campus wire. You can read and learn about that. Okay, stop here. Thank you guys. Any questions, comments? Okay, it was great having you and then teaching this class. Good luck in the final. Keep in touch. Have fun.